here. Okay, that's pretty good. Okay, so the problem was 19.3 is about M&M consumption. And it says, here is the data from 19.1. And now let me see, make sure that you can kind of actually see everything that I have up here. Are you looking at that a PDF of that I sent you the data? Is that what you're seeing right now on your screen? Yes. So it's got like the curve here and everything. Okay, great. Okay, great. So I gave you the key data here from our when we did this problem. The mean is 50.15. The standard deviation is 30.31, and the sample size was 20. So this was from the sample that we did or that they did of the students and how many M&Ms that they took. So let's go back to the problem here. So state and comment on the technical conditions for the validity of a one sample T interval with these data. So let's just see what somebody got on that one there. 5, 1, 25. So Ariel, are you here? Nope, Ariel. You are here. Okay, that's good. Okay, so what did you look for the technical conditions on this?
So I wrote, so since we're looking for a T interval, it has to be, the sample size has to be less than 30. And then I also wrote that the sample must be randomly drawn. And that's all that I wrote. Okay.
Well, that is an almost complete answer. So let's just kind of take a look at the solutions manual here and see what they gave as a solution on this one here. So for A, it says, so the technical conditions for this sample to produce the result, for us to be able to make an inference for the population from this sample, is that it has to be random. So don't forget that. That's like super important. And either the sample size is large, n is greater than 30, or the population is normally distributed, one or the other. So if I, let's see if I can actually write on this. It's possible. Yeah, it's possible. Okay. So we weren't told how it was sampled, so how the sample was selected. I don't know. I would guess if they're giving it to us as a problem, it's okay to think that it was that part was done correctly. The sample size was small. It was less than 30, so it's not greater than 30. And she says it does not appear to be entirely normally distributed. So I kind of went back and looked at the picture. This is the picture of the dot plot there. And although it's pretty widely spread out, if I was looking at that, I would kind of say, well, you know, maybe it's not entirely normal, but I would kind of say it's like normal enough. So that would be my take on it. You know, kind of most of the stuff is happening, you know, like right here, and let me get a thing here. Come on, draw for me. Most of the stuff is happening in here. Yeah, it's not exactly in the center, but you know, this is a, you know, so, you know, I mean, given that it's a small sample size, I would say that it's normal enough. And since I'm going to use a T distribution instead of a Z distribution, I'm kind of okay with it. It's not like super crazy skewed, and I don't need to worry about that. Are we okay with that? Yes. Okay. All right. But you do need to, okay. I'll leave it at that. I'll leave it at that. Then let's look at the next part of the problem. Okay. So calculate and interpret a 95% T confidence interval for the parameter of interest. Well, we kind of did that when we were doing the problem before. So did anybody do it? Somebody want to volunteer to answer this part? To make the T distribution? You want to go for it again, Ariel? Okay, what'd you do?
So at first I started to find the t-value because the interval formula requires it. But then I realized that it was 95%, which is part of the empirical rule. So I just put, so I realized that it was the 97.5 like percentile thingy.
Right.
And since it was the empirical rule, I could just look at my distribution and like see the values for the interval instead of like doing like the formula.
Okay, so you used like that table that we used before to find it for a 95%?
I did like, I don't know if you can
hold it up.
see.
Can you hold it up closer? Nah, I can't see it. Nobody else can see it. If I can't see it, nobody else can see it either.
Okay.
What did you get for your t-value over here?
So I didn't do the t-value because it was the empirical rule.
Okay.
So like I made my distribution. So at the center for the mean, I had 50.15.
Yes.
And then the S that was given was 30.31. So I added it. So that became 80.46 for the first standard deviation. And then for the second standard deviation, it became 110.77.
Okay, I'm going to stop you right there. Okay, because you made the same mistake that I made the other like 2 classes ago, which is a totally reasonable mistake. But let me see how to describe this. This is a sampling distribution for samples of n equals 20, right? So if we're trying to find our now they gave us a standard deviation of, what was it, 30.15?
30.31.
30.31, sorry. They gave us a standard deviation of 30.31, right? But if we're trying to find this, the distribution of a whole bunch of samples of n equals 20, then we get to take this standard deviation of 30.31 and divide it by the square root of n.
Oh, I forgot. Okay.
It's the same mistake that I made. If we, that actually is correct. This is not correct, and that is not correct. So let me go back to here. This was 50.15. Yeah. If we're finding our sampling distribution, this would be if I was making the distribution like based on a sample size of 1, but my sample size is 20, I got to remember to divide it by the square root of n. And when we did that the other day, we got a standard error here of 6.78. Okay. So I'm going to come back over here, and I'm going to say our standard error of our mean is 6.78. So my standard deviations are going to, I think I probably have them here. They are going to look like, yeah, 56.93 and 63.71. So 56.93, and then what was it? 63.71 on that side, and then on the other side, it's going to be 43 and 36. 43, 36. Get rid of this here. 43, 36. Those are going to be 2 standard deviations the other way. Okay, again, I'm going to stop here, and I want to make sure everybody's following here. Is there a question? No, we're still pretty good. Okay, so that was my standard deviation. Let's go back to the problem and see where we were. All right, so I need to find the 95% T confidence interval. Well, so I'm going to make a statement here. When we're dealing with quantitative variables and we're talking about confidence intervals for the mean, forget about the empirical rule. I mean, you know, maybe not entirely forget about it, but the empirical rule is for normal distributions, and we don't have a normal distribution. We have a T distribution. So it might be kind of close to the empirical rule, but you're really going to have to calculate it out based on your degrees of freedom, based on your sample size. So Ariel was correct in saying that the 95th percentile, you know, I'm going to go over here. I go from here to the middle, and it's 50%, and then here to the other end of the 95 percentile is 47.5%. So I am looking at the 97.5 percentile, or I'm looking for 0.975. So in order to find that T value, I got to go to my calculator. And I'm going to go second distribution, inverse T. And I'm going to put in 0.975 and then a comma. And then my degrees of freedom is n-1, so that's going to be comma 19. And I find out that my critical value here at this level of degrees of freedom is 2.093. This is my T, my critical value T. So I'm going to stop there again, and I want to make sure everybody's following what I'm saying here. I'm seeing yeses. Okay. Give me just 1 second. I'm stopping sharing here for just a second here, and okay, got it. All right, we'll come back to share this again. Okay, all right. So my confidence interval is going to be my X bar plus or minus wait. Yeah, plus or minus my critical value times my standard error. It's going to tell me what number is that going to be over here. So I have 50.15 plus 2.093 times my standard error, which is 6.78. So this number over here at this end of my confidence interval is going to be 64.34. And the number at the other end of my confidence interval is going to be minus that. So at the other end, it's going to be 35.95, 35.96. So my confidence interval, I would write, as 35.96, comma, 64.34. So again, let's pause and make sure everybody's with me here. Somebody want to ask a question?
I have a question.
Please.
Which part is where where did you find the SE?
The SE is the standard deviation from my sample divided by the square root of the sample size. So if I take 30.31 and I divide it by the square root of 20, I get 6.78.
Okay. I understand, like if I punched it into a calculator, like you'd get 6.78.
Mm-hmm.
And I do have that formula. I guess I didn't know when to use it.
Okay.
I got tripped up.
So,
Okay.
Here, let me try this, Bella. I take a sample of 20, and I get a mean of 50.15 M&Ms, and in that single sample of 20, I have a standard deviation of 30.31. There's a pretty big spread. I have one sample of 20, and if we go back and look at the dot plot, you can see it's pretty spread out. I mean, it goes all the way from less than 10 to more than 100, right? I mean, it's a big spread there. That make sense to you?
Yeah.
Okay, but then I'm not just looking at that one sample of 20. I'm making a distribution of essentially an infinite number of samples of 20. And if I sample 20 people over and over and over and over and over and over again, I'm going to have a lot more of those people are going to be kind of concentrated around the middle, and it's not going to be spread out as far. Does that make some sense?
Yeah.
Are you sure that makes sense?
Yeah.
That's why I get to divide the standard deviation from my sample by the square root of n. If I divide it by the square root of n, I'm making that standard deviation smaller. I'm bringing it in, right?
And you want to make it smaller?
I would like to have zero variability. Then that would tell me automatically exactly what the population is. I want to have zero variability. I'm never going to get there, right?
Yeah.
But if you think about it, if my sample size was all the students in the world, right? And I took that sample over and over and over again, I would get the exact same mean every single time, wouldn't I?
You should.
Right? So, yeah, I mean, unless somebody was hungry or less hungry on a particular day, but let's just say I did it, you get the picture here, right? I would have zero variability, right? Because my n would be so monstrous that dividing this giant number into this standard deviation would make it like almost zero.
Okay.
You there?
Yeah.
Okay. So I always need to take the standard deviation that I get from my sample, and when I'm making my sampling distribution that looks like this, I definitely have to divide it by the square root of the sample size. Otherwise, I'm not really getting an accurate picture.
Yeah. Okay.
Okay. Tough concept. Tough concept. All right. So back to 19.3, the problem. Okay, so write a sentence interpreting what the phrase 95% confidence means in this context. So who wants to volunteer me a sentence here? What does this mean? What have I just shown here in this diagram that we just did by coming up with this with this 95% confidence interval right there. Somebody give me a sentence. I will take a volunteer. No volunteers? So I have to use the magic bowl for volunteer? Oh, magic bowl. Well, let's see if we can get one. Let's try it. Okay, so Natalia, can you give me a sentence here? Are you still here? Yes, you are. I see you.
I think she's in the restroom.
What? Did she check out?
She told me to tell you that she was in the restroom.
Okay, but I see her right now.
I just got back.
Okay,
I
good.
don't know
okay,
what's going on.
That's fine. Then hang on. Okay, good. Hang on. So Cassandra, can you give me a sentence? What does this mean? The 95% confidence interval. What's it telling me?
You are 95% certain.
Wait, I can't hear you. A little bit louder.
You're 95% certain that that students will get between 35.96 and 64.34.
Yeah, I mean that is close enough, right? I am 95% certain that the actual mean, if I go take a sample of the actual mean of the student of the population, they're going to want somewhere between 35.96 and 64.34 M&Ms, right? And since we can't divide M&Ms, in pieces, somewhere between like 35 and 65 M&Ms. That's what they're going to want. I am 95% sure that the actual population mean lies between those two numbers. Yes? Yeah, I'm seeing slow nods. Yeah. Okay. All right. Let's go back to the problem. How does this interval compare to the informal interval we calculated in part H of 19-1? Okay, so I'm going to just kind of look at that picture right here. And when we did 19-1, we used a confidence interval. We were first doing it like approximately 95%. And we were using the second standard deviation. We were using the empirical rule like Ariel wanted to do, right? But if we were using the empirical rule on the one that we're doing right now, we are a little bit outside. Our confidence interval is a little bit wider than what the empirical rule gives us. And it's wider because we're using the T table and not the Z table. The T table kind of gives us a little bit more wiggle room on the ends than the Z table, than the normal model. The T model is going to give us a little bit more space than the normal model. So if I say 95% on the empirical rule, that's different than 95% on the T value. The T value is a little bit wider. All right, let's keep going here. All right, so I'm just going to ask this as a question. And we'll go to the magic bowl here. Magic bowl is asking, no, I don't like to duplicate. This is not good. Okay, Alyssa, you hear Alyssa? I saw you pop in. Can you hear me? Calling Alyssa. Did you walk away? Okay, we'll call you later. Annie. So Annie, I want you to help me with this. If I want, so this is my 95% confidence interval. Is a 90% confidence interval going to be a smaller interval or a larger interval?
Would it be a smaller interval?
Indeed, it would be smaller, right? And if we just look at it on the chart, if this is 95%, well, let me make a new chart here because I don't want all these lines. But if if 95% is there, well, then, I mean, you know, sure enough, you know, 90% is going to be a smaller interval, right? I mean, it's got to be a smaller space on the graph, right? And correspondingly, you know, 99% is going to be bigger because I got more space. I'm more confident. I'm more confident. I got a larger interval that I'm sure is going to work for the population mean. Make sense? Yes? No? I mean, the picture, I think, really helps understand. I wouldn't want to have to memorize this without a picture. I really like the picture. So, okay, but here's a little bit different question. All right, so let's say I still had, let's use another page here. So no, let's use this page. We'll stay here because we got all the material here. I still have my X bar is 50.15. So this is going to stay the same. And the standard deviation is going to stay the same. But my n, let's say that my n, instead of being 20, was equal to 200. What would my confidence interval look like? Would my confidence interval be bigger? Or would it be narrower? Yeah, Yvette, tell me.
It would be narrower because the larger your sample size, the less variability you have.
Does everybody see that? If I was dividing 30.31 by the square root of 200, well, let's just do it and see what we get. So I take 30.31 and I divide it by the square root of 200. Well, now my standard error is only 2.14. I'm going to have a much smaller confidence interval because I have a much larger sample size. Larger the sample size, less the variability. Yes? Couple thumbs up. Okay. Back to the book here. Okay, so part I. Part I says, suppose the sample size had been 200, but the distribution, instead of being kind of maybe normal, I mean, the distribution was really skewed. So the distribution, you know, the distribution looked like, you know, like that or something like that. So like way skewed, right? Can we still use the t-interval calculation? So Ariel's saying no. Natalia, what do you say?
I would say no, because the sample size is large enough to like cancel out the skewed population. So it doesn't have to be normal because the sample size is so big.
So you're saying that the t-interval calculation would still be valid or would not be valid?
Would still be valid.
Would still be valid. Yeah, because Ariel, sample size greater than 30, right? That then if sample size is greater than 30, I don't really have to worry about whether the underlying population has a normal distribution or not. If the sample size is greater than 30.
I thought that.
Go ahead, please.
I thought that for a skewed distribution, you'd have to use the median instead of the mean.
Okay, so Great. This was excellent. Okay. So if I have a population and my distribution is skewed, right? And I am describing the distribution. I'm just describing the distribution of the data that I got. I have to talk about shape, center, and spread. And in this particular case, the shape is skewed right. And you're right, if it's skewed, my center is the median and my spread is the IQR, right? That's if I'm describing a distribution. But what we kind of shifted to, this when we started talking about the central limit theorem, is we're not describing a distribution of a population. We're describing a distribution of samples from this population. So if I take a sample from this population and I take like a whole bunch of different samples from this population, and I say, what's the average, say the average size of every one of these samples? And I plot those averages. So I'm not plotting the different data points. I'm plotting the averages of the samples. You follow my leap here? That distribution is going to be normally shaped. If the sample size is greater than 30.
So the T would be valid then.
The T would be valid then, because the sample size was greater than 30. Right? A lot of different factors here to kind of remember. But you kind of got to go back to where we made that leap from just looking at a population to looking at a distribution of statistics from that population. We're looking at a distribution of, say, averages. So let's take another example here. Well, okay, let's think about our remember our pennies example, where we looked at how old pennies were? And the distribution was like really skewed, right? Because we had a whole bunch of pennies that were pretty young, but as we got older and older pennies, there were fewer and fewer of them. You remember that? Everybody with me here on that? Remember that example? Yes? So the distribution of the population was skewed, but if we took samples of, say, 40 pennies, if n equaled 40, and we averaged out the age of those 40 pennies, and then plotted the average age of those 40 pennies. So I'm plotting the average age of my samples. That distribution is going to be normally shaped. Okay. Reasonable enough? I'm gonna move on to the next section. Is that okay? Yes? No? All right. Let's just do it here. So okay, and this is actually gonna help us because we're gonna follow a lot of the same processes, except, can you hear that noise? Can you hear the lawnmower going in the background, or is that? You cannot hear it. You can hear me pretty clearly. It's not. Yes. Okay, great. Okay, that's fine. Because it's like insanely annoying. I can't handle it. Okay, that's better. Okay, here we go. Topic 20, test of significance. So this is p-values now. We did confidence intervals. Now we're doing p-values, but we're doing it for means. We're doing it for quantitative data. Right. So we're really, well, we're going to focus on objectives 1 and 2. We're not going to do objective 3 for this, right? We're going to look at all aspects of a test of significance concerning a population mean. We're going to do null hypothesis, alternate hypothesis, test statistic, p-value, the same thing that we did for proportions. And we're going to talk about what conditions are necessary for this to be valid. But I think you're going to find this to be very similar. So backpack weights. So this is a Cal Poly San Luis Obispo student carrying a backpack. Why are her jeans all torn up? I don't know.
Fashion.
Fashion. Is that still fashionable? Is that still fashionable, or is that old school now? I don't know. Tell me. It's still fashionable to have torn up jeans? Yeah?
It is.
That one's really stuck around for a while. Torn up jeans. I used to love getting a new pair of jeans. Now I don't like jeans at all. Okay. Okay, so we recorded the body weight and backpack weight for a sample of 100 students. And it's in a file called backpack. I don't think we're going to need it right now. They wanted to see how well Cal Poly SLO students adhered to recommendations to carry less than 10% of their body weight in their backpack. Okay. So we're going to find out whether their data shows that the mean backpack to body weight ratio is less than 0.10. So let's just make sure we understand the problem. If I have weight of the pack divided by weight of the person, that gets me a ratio. And we want that ratio to be 10%. Well, we want it to be 10% or less. So that would be 0.10. Are we following the problem here? We understand how it's being stated, yes? Okay, all right. So we're going to do a test of significance, the same thing that we learned in topic 17. So, they gave us some nice statistics right here, and they gave us a dot plot of the distribution as well. So they're telling us that the mean ratio was 0.77 of their 100 students. So there's 30,000 students in a Cal Poly SLO. So they only took a sample of 100, but of that 100, the standard deviation among them was 0.0366. So this is what it looked like. They had some people that were clearly not carrying anything in their backpack except maybe their lunch. And they had a bunch of people over here, well, a handful of people over here that were carrying every book that they had for the whole semester. And then everybody else is kind of like in the middle there. And just notice right here, they put 0.10 kind of right there in the middle of this dot plot. So we're going to ask a question. We're going to ask a question of, Cassandra, you've come up like 4 times. My random number generator, the magic bowl is much more random than this. So I'm not going to call on you, Cassandra. I'm going to call on Kaylin. Kaylin, are you here?
Yeah.
Okay. So just looking at the picture here, we're trying to find out whether or not the ratio of backpack weight to body weight is less than 0.10. So looking at the picture here, does it look like that's probably the case?
It's less than, correct?
Yeah. Does it look like for the most part, more people have less than 10% of their body weight, or more people have more than 10% of their body weight?
Less than.
I would say it looks like less than to me also, right? This part of the dot plot has a lot more dots, And when I look at my sample statistic, the mean that I got from my 100 students was less than 0.10. So yeah, I mean, I'm thinking, hey, it looks like it's less than 1.0. Let's see if it works out statistically. So I need the parameter of interest. I'll take a volunteer. Who wants to give me, what are we trying to find out in this study? What is the parameter that we are trying to discover? Parameter deals with a population. What is the parameter that we're trying to discover here? Keely, tell me, what's the parameter? You hear, Keely? Yes, I see you up in the corner there. What's the parameter we're looking for here?
The students.
Okay, so that is the population. So the population is we're looking really for SLO students. And what are we trying to find out about SLO students?
Oh, the weight. I don't know.
Let's go back to the problem. The problem is saying, right here. Let's do it right here. So here's the problem.
How well they adhered to the recommendations.
Okay, so then tell me, I have a null hypothesis. How am I going to write my null hypothesis? What is my null hypothesis? This is now remember, the null hypothesis always has an equal sign, and the alternative hypothesis always has either less than, greater than, or not equal to. So can you tell me what that would be? I'm asking you still, Keely, for the null hypothesis.
Pi. Does this have? Oh, okay. Pi is equal to 0.10.
You've got the right concept, but you're using the wrong symbol. Pi would be for a proportion. What symbol are we going to use when we're dealing with a mean?
Oh, X bar?
No, X bar is the statistic.
Oh,
We're trying to find the parameter here.
I don't know.
Yes, you do. You're running out of options. So you know it's not pi, and you know it's not X bar. What is it going to be?
P hat?
Nope. Then you got one more left. Go for it. Think of a cow.
Mu.
Mu, right? I'm trying to find out where the average ratio of backpack to body weight. My null hypothesis is that it's 0.10. So what is my alternative hypothesis? Sasha, are you here, Sasha? Yes, you are. I see you down in there in the corner. What's my alternative hypothesis? Oh, maybe Sasha disappeared. Okay, Lily, can you give me my alternative hypothesis?
M is greater than 0.10.
Well, let's look back at the problem here. So read the sentence in the blue, or the one that I highlighted with the green. What?
Less than.
Less than. That's right. My hypothesis is that no, I'm thinking that the average in the population, the average ratio in the population is less than 0.10. So I get this whole first part by reading and understanding the problem. Oh, in fact, we just did it down here. All right, so we did this part right here. Question. No question. We're good. Okay, proceed. Okay, well, what are the requirements for the central limit theorem for a sample mean to be valid?
Wait, sorry,
Yeah.
Mr. Jenkins, I do have a question.
Good, please.
Why is the alternative hypothesis, well, is the alternative hypothesis based on your data, like that you can see that there's more underneath the null hypothesis value? Because I would have thought that the alternative hypothesis would have been that it's greater than that, because in the study it says they wanted to see if they adhere to the recommendations to carry less than 10%. So they're saying that they expect people to have more than 10%.
Oh, so Maddie, let me think here now. Let me see. Let me see what you're saying. You're saying that they expect. Okay, we agree on the null hypothesis, right? That the null hypothesis is that it's equal to 0.10, right?
Oh, wait.
Yes.
Yeah, Evelyn, go. Yeah.
So I thought the alternative was supposed to be like kind of the exact opposite of the null hypothesis. And in that case, wouldn't it be similar to what Maddie was saying, but except the null hypothesis would be less than, and we're testing to see if it was greater than?
Well, so the null hypothesis is always going to be that it's equal to something.
Oh,
And
okay.
so here's how I'm thinking, and you know, and then we'll look and see what Beth says, right? Because you know, I'm not always right, as you're well aware, right? But I know that I'm going to have a picture, and it's going to look like that. And in the middle here is going to be my mu of 0.10. And I already know that my test statistic is 0.077, right? So I know that my test statistic is over here somewhere of 0.077, right? So I'm thinking what I'm trying to find is what is the if the average is 0.10, what is the probability that I'm going to get 0.077 or less randomly? That's what I'm thinking.
Okay, that makes sense. Yeah.
Does that make sense? Let's confirm it though. Let's go to the solutions manual and see. So this is 20-1. I need to go over here. No, let's see. I have the solutions manual. No, okay, I got to get the manual. So for solutions manual, and let's search for 20-1. No, so the alternative hypothesis is that the population mean ratio backpack weight to body weight is less than, that should be 0.10, not 0.01. In symbols, alternative hypothesis is mu is less than 0.10. So that is our hypothesis. And you know, part of the way that I would determine whether it's like less than or greater than, because I certainly understand what you're saying. I'm pointing at you, Maddie. You're up here in my, I don't know where you are, where I am on your screen, right? But you're up there, right? Is when I look at my test statistic, I know what my center is going to be. I know that my center is going to be mu at 0.10, and my test statistic is to the left of that, right? It's on the less than side, and that's kind of how I help place it.
Yeah, I had always based my like alternative hypothesis on the what the research like study was about, but I guess I should just base it on the numbers and the test statistics.
Well, I mean, so explain to me again how the research. Explain to me how you were looking at it again. I just want to understand this a little bit better.
No, it's just the way that I read that they were trying to, wait, let me find the sentence.
Okay.
Trying to see how well Cal Poly students adhered to the recommendations to carry less than 10% of their body weight.
Mm-hmm.
So in my mind, I was thinking, oh, they must think that people are carrying more, because people always say that students are carrying like really heavy backpacks. I don't know. That was just kind of like my thought process. And that was it, basically.
Yeah. Yeah. So I guess what I would say is, you know, I'm gonna actually ask that question of Beth and see how she would, you know, respond to that. Because let's say we didn't have a test statistic to start with, right? Well, yeah. So if we didn't have a test statistic to start with, but we just posed the question, I mean, you could pose the question and say, well, you know, are they carrying more than 10% of their body weight, and have that as your alternative hypothesis? I'm guessing that if you did that though, then when you actually took your statistics, you would find that that your p-value was like this humongous number over here. You know, so yeah. I'll have to think about that a little bit more. That's good. Okay. All right. So we're asking for the requirements for the central limit theorem to be valid. So what requirements am I looking for here? I'm looking to ask, oh, Maddie, you get to answer this question. The magic calculator called your number.
Okay. I'm not sure actually.
Okay, so were they randomly selected?
Yeah. Yeah.
Well, they say they got a sample of 100 students. I think we just kind of need to assume that they were randomly selected, right? So that's one characteristic that has to be true for the central limit theorem. So were they random?
Yes.
And we'll assume yes. And what's the other one? It's quantitative.
It has to do with the sample size. And you multiply it by the mean? No.
Easier.
It's greater than 10.
No, close. That the 10 is when we were doing proportions, was p hat times 1 minus p hat had to
it's
be
greater than 30.
Greater than 30. That's right. Yeah, it's greater than 30, right? So we satisfy both of those. Are we okay with that?
Yes.
Yes. Okay. All right. So so we need to calculate the standard error of the sample mean to approximate the standard deviation of this distribution. So let's go back to our data right here. There's our data. Our n is 100. So go ahead, tell me what the standard error is. Do a calculation and find out tell me what the standard error is for this distribution.
Mr. Jenkins?
Yes.
I don't know if I'm supposed to use the S over radical N, or if I'm supposed to use like square root P hat parentheses 1 minus P hat over N. That's
Okay.
where I'm confused.
So p hat deals with proportions. That's
Oh,
categorical variables. We're dealing
Yeah.
with means,
which is quantitative.
quantitative, right? So
Okay,
so you're going to use the S, Bella. Yeah, good.
thank you.
Sure. Clara, did you get a number?
I did not.
You did not. Okay. Do you know how to do it? How would I find the standard error here?
Okay, you have to do SE equals, and then it's the square root, and it's wait.
I'm assuming she went to go get notes and that she didn't just walk out on the class, did she? No, Clara wouldn't just walk out like that.
That would be funny though if she did.
I'd be worried.
If she didn't know it and she just walked out to avoid answering it.
Yeah. Well, I'm gonna let somebody else help me set this. Oh, here we go. Clara, I was afraid you just walked out on this, you know?
So it's like, is this the one with p hat?
No, this is a quantitative variable.
Okay. So it's the one with the mean?
This is with means, yes. So I need to find the standard error.
Okay. So it's like, is it the mean times 1 minus?
Nope. Okay, I'm going to ask you a question, Clara. Are you with me?
Yes.
I'm trying to find the standard error. And do you recognize that the standard error is kind of like what we use for standard deviation when we don't really know the actual standard deviation? We're just trying to find it based on our statistic. Are you clear on that?
Mm-hmm.
Okay. So if I'm trying to find the standard error, which is kind of like the standard deviation, and I will tell you right now that the denominator is going to be the square root of n. Right? What do you think the numerator is going to be? If I'm trying to find something related to standard deviation, what's going to be the numerator?
The mean?
Nope. How about the standard deviation from my sample? No.
Oh.
So if I'm trying to find the standard error of something quantitative, I'm going to take the standard deviation that I got from my sample and I'm going to divide it by the square root of the sample size. Did somebody get a number here? Yeah, Sitlali, what'd you get? I have to unmute Sitlali.
Sorry.
Okay.
For S, I used the 0.0366 over the square root of 100, and that gives me 0.00366.
0.00366. That would be my standard error. All right. We're gonna come back to this. We'll start right here on Friday. But let me just, before you go, I wanna go over something here that inference key points. I think this is, I sent this out here, and I want to go, I sent this out, it's like a packet of like 7 pages of like the key things that I think you need to solve these problems for proportions or for means. So let me just say, let me make one more picture here so you can kind of see this. Categorical data deals with proportions. What proportion of M&Ms are blue? What proportion of the people are female? What proportion of the people are Latinx? You know, those are proportions. Those are categorical variables. How many people are left-handed? You know, those are proportions. And for proportions, we're using pi for the population, and we're using p hat for the sample. Quantitative variables, we're trying to find the mean, you know, or what we more commonly call the average. And for that, we use mu for the population, and we use x bar for the sample. We use, on proportions, we use, no, I'm going to leave that right there. For mean, we use S, I'm sorry, I don't want to do that. We use sigma for the population standard deviation, and we use S for the sample standard deviation. So if I just come back to this inference key points, I broke it up into what I thought were pretty logical sections, and these are the key things that you really need to know. Confidence intervals for proportions, got a little page there. Confidence intervals for means, got a little page there. So it gives you the key formulas and the key conditions that you need to know. Then I got a couple general points about confidence intervals, mainly dealing with margin of error. And then tests of significance for p-values. And see, do I have this for? Yeah, I have some general points of for tests of significance for p-values. It talks about null hypothesis, alternative hypothesis, technical conditions. What is a test statistic? What is a p-value? How do you make a decision? And then I have the specific formulas and stuff for proportions, categorical, and for means, quantitative. So it's a really nice summary, and you know, in the course of your studying and doing some problems, I would say, like, refer to it. Okay? All right? Come on, guys, hang in there. We're like, how many more class sessions do we got? Let me see. We got like, oh, geez, you know, we got like one more full class session. Like, that's it. And then we got another day here. I'm going to let you work on the test that I'm going to hand out on Friday. So, you know, like, just push it through the tape. You know, that's what we used to say in track. You know, is when you're getting towards the end of the race, the tendency is to kind of let up just before you hit the finish line, and that's when the guy that you hate, who's running right behind you, like zooms in front of you and beats you, right? So you always have to run. And your finish line, you put it like about, you know, 5 feet past the tape. So you just kind of got to run through the tape. So just kind of like push your way through the next couple of sessions. All right, that's my pep talk. Go to your next class, wake up, go get a cup of coffee. All right, Clara, hang out for just 1 second, okay? All right.
Thank
just like-
you.
yeah, you're welcome.
Thank you.
You're very welcome.
Thank you, Mr. Jenkins.
You're welcome.